Today we'll talk about Rayleigh-Bernard convection Lorentz model, which is supposed to be an example of, illustrate some of the concepts from yesterday. Okay, we started this yesterday. We discussed how the Rayleigh's basic understanding that is still the basic qualitative reason why heavy over light is unstable. We discussed the exchange. Everybody remember that? Anybody not remember that?
Well, I wasn't here.
You weren't here. Okay, we'll discuss it after, during the break. Okay. And we wrote down the equations of convection, which are the Navier-Stokes equations. Let's see, what did I use yesterday? Oh, I just took this thing here yesterday and I walked around with it. Right. Navier-Stokes equations, where usually we take out the gravity in Navier-Stokes equations, the reason being that it's usually absorbed into the pressure. But here we don't, because the density, which appears as a constant here in ordinary Navier-Stokes, has a temperature dependence and is thus responding to the temperature equation. And then comes the equation for the temperature. And what we did was we found the base state. The base state satisfies these equations with no motion, before that, we put on the boundary conditions, which are that the velocity be 0 at the top and bottom, and the temperature be fixed at top and bottom. And we found the base state, which is motionless and has a linear dependence going between T0 and T1 from Z equals 0 to D. And then we found the equations in terms of deviations from the base state, which has a star. The new equations are for the hatted quantities here, and we just substituted into that, and then we non-dimensionalized, and where we left off was approximately here, we'll say. Yes, we'll say here. So, yes.
Is there a lecture slide yesterday?
Are there? Oh, I'm sorry.
Oh, there is.
Yes.
Thank you.
So if I go over the steps that we have and will accomplish concerning convection, so it does not seem endless. Oh, why did that stop? Hello.
It looks like the connection just gone loose.
Connection came loose?
Oh, it's back.
He's better.
It's back.
Yes, okay, right, so I'm going to push it harder, there. Okay, so the steps are the Boussinesq. Yeah, okay, the Boussinesq approximation, which sets out the equations, the basic equations, and then we found the basic state and non-dimensionalized, and we discussed the boundary conditions. And again, for those, who else was not here yet last time? 1, 2, 3, 4. So 4 people. There
was a class at Melbourne Uni that we had to attend.
Yes. No, I'm not blaming you. I'm just thinking what to do about this.
It's recorded.
We'll catch up.
It's recorded still. Well, okay. Okay, so we're at the stage where we're discussing the boundary conditions, and we're going to do linear stability analysis here. So the basic equations, which were here, the Boussinesq equations, right in the middle here, have been transformed to these equations here, which are non-dimensionalized and contain only 2 parameters, the Prandtl number and the Rayleigh number. And now we're discussing boundary conditions. And boundary conditions are often given short shrift. I like something that I read a long time ago in a book by Roach, which is this. People say, oh, the equations go to, and then the boundary conditions. But all fluids everywhere obey Navier-Stokes equations. The ocean, the air, I mean, the only thing that really defines a problem is the boundary conditions. The boundary conditions are not just a detail, they're the main thing. So anyway, let me discuss then the boundary conditions. We're going to do the simplest possible thing, that which was done before there were computers and which is still done for any kind of qualitative understanding, which is to assume a horizontally infinite domain. And we're going to assume for solutions that they be periodic with an imposed wavelength of 2 pi over q. This q is the wave number. In the vertical direction, we are going to impose t equals 0. Why t equals 0? Well, that was discussed here. That is to say, the basic boundary conditions are that t be hot here and cold here, but that was already satisfied by the base state, which interpolated between the value at 0 and the value at 1. And hence, when you discuss the deviation from the base state, if the total t is supposed to obey these t0 and t1 boundary conditions, and the t star obeys those conditions, then the t hat had better obey conditions 0 and 0, so as not to change the fact that the t and the t star have the same boundary conditions. As for u, it always had 0 boundary conditions, meaning that you are not, that there's no velocity at the plates, which is going to be discussed in just a moment. And for those of you who weren't curious, it is good because by then people were getting tired, I was getting tired, so I didn't discuss it very much, even though I claimed to have. So this I'm going to do in a little more detail. So we have t equals 0 and t equals 0, and that means that the temperature, that the temperature of the perturbation is fixed at 0, 0, so as not to change the fact that the t is t naught here and t1 here. And w equals 0 means no penetration, and that you really have to do because, after all, if you hit the wall, it's not much of a wall, is it? Or forget about the wall. If you hit the surface, it's not much of a surface, right? That's what a surface is you're not going
So
to.
T and temperature and velocity now are the perturbation.
Thank you, yes. I have dropped several things. Thank you for saying this. That is to say, I introduced notation after notation. We started off with a T and a U, but then we made a star that was the base state, and then we defined a hat that was the deviation from the base state, and then we defined non-dimensional quantities with bars, so we went from nothing to a star to a hat to a bar, and now we're just going to drop all those things and go back to the U and go back to notation that has nothing at all. So that means the non-dimensionalized deviation. Thank you. Okay, so you don't go through the surface, otherwise it wouldn't be much of a surface. And the gesture I made before is that the boundaries, if you have rigid boundaries, you also have no tangential velocity at the top nor at the bottom. So the u and the v are also 0. And by incompressibility, that is to say, dxu plus dy dv dzw equals 0, if u is equal to 0 every place here, and v is equal, then the x derivative is also, you always have to be careful with boundary conditions not to take normal derivatives. Right? You could not take a z derivative of that, because it just happens that u is 0 here, but the z derivative is not necessary. So, but since u is 0 every place here, you may take a derivative in either the x or the y directions, because it's true every place. It's not true for all z, but it's true. So you can take dxu and say that that's 0, and dyv and that's 0, and that leads to the result that dzw is 0. So that's what's written here. So that's the realistic case of having rigid boundaries, glass or something, so you can see through. But that leads to having to have boundary conditions w equals 0 and dzw equals 0. And the simplest kinds of functions that are trigonometric functions. And of course, trigonometric functions do not have their value and their derivative being 0 at the same place. Basically, the derivative is off phase with the value. So that's not convenient computationally, and hence, what is often done is to impose instead the condition of no tangential stress, like a free surface. A free surface obeys, okay, this thing here is the tangential stress in the y direction. Notice here the crossed derivatives, dz of the x velocity, dx of the z velocity. Okay, and then here you have the crossed derivatives in the other direction. And so you manipulate that in the same way. That is to say, since w is equal to 0 every place along the surface, then that's true of dxw and dy of w as well. So these things go away. These terms dyw, dxw go away. So you have dzu being 0 and dzv being 0. And now if you take the x derivative of this term, and you can do that because this is true for all x, and you take the y derivative of this, because again you can do this because it's true for all y, you find these other things are 0. And now you can write that again you can use incompressibility, take the z derivative of incompressibility, that is to say this equation here, take the z derivative of it, and that you can do because it's true everywhere. So the second z derivative of w is minus the z derivative of dxu, and this is plus the z derivative of dyv, and so if we do that, we find that that is 0. So the boundary conditions in this case, the free surface case, are that w be equal to 0, no penetration, and also that the second derivative of w be 0. And that is easy because that's what trigonometric functions do. Their second derivative, if you have sine, its second derivative is minus sine, and it's 0 also at top and bottom. So that is much easier computationally. Functions that satisfy w equals 0 and dzw equals 0 are Chandrasekhar functions, the great astrophysicist / fluid dynamicist, who Nobel Prize winner, who I won't say founded, but followed in the steps of people like Rayleigh and Taylor, and as one of the great founders of hydrodynamics and continuum linear stability theory. Anyway, so he did, those are the functions that you would really need are called the Chandrasekhar functions after him, but we're not going to do that. We're going to use instead trigonometric functions like sine of k pi z. That is, it's not merely sine that is 0 here and its second derivative, but also sine 2 pi z and sine 3 pi z and all those sines. Okay. Now, free surface at the top is realistic. You could be heating, and I mean, it's best to have a plate on top because then you can really cool it. If it's a free surface, it's a little harder to impose uniform temperature, but let's say you can. But a free surface at the bottom is rather difficult to do. Your fluid would then fall down. So it's not realistic, but it is the analysis that is done and leads to the right qualitative understanding. Okay, so we continue. Now we're going to simplify further and be merely two-dimensional. That's to say, every place I've been making motions with my hand, I've been talking about the z direction, where there's the plates here, that we need. I've been talking about derivatives with respect to x and with respect to y. But now I'm going to assume that everything is independent of y. Again, this is going to give you the right kind of qualitative understanding you need, and the calculations are simple. So we're going to have independence of y. In this case, you can write the velocity, you can, by construction, to be incompressible by making it the curl of a stream function with whose vector direction is in the y direction, and which depends on x and z. And then you have the, how many people, I don't know, this is basic fluid dynamics, it has nothing to do with dynamical systems. People who have studied fluid dynamics, I must have seen this before. So if you write u as a curl, then of course its divergence is 0 because divergence of curl is 0. If you have no penetration, as we said, which is always necessary, w is 0, hence dx psi is 0, meaning that psi does not depend on x, meaning it has a constant value here and here, meaning that this is a streamline and this is a streamline. You know that the velocity is along streamlines. Then we're going to need more conditions to impose on psi. Let us look at the horizontal flux. We integrate the horizontal velocity from the bottom to the top, and u is dz psi, as written here, minus dz psi. And of course, if you integrate dz psi from 0 to 1, you're going to get the difference in the psi values, and that's psi naught minus c1. And hence, you found that there's a constant value here and a constant value here, but the difference between those constant values is determined by the flux. If, as one often does, you impose that there be no flux, then that says that there is no difference between the two. And one of the values is arbitrary. You can see, of course, that you can add any constant to psi and get the same velocity field. So you could always have set psi naught, say, to 0. And then if you impose 0 flux, then you have psi 1 equals 0. That's not the only possible choice. You can also have impose a different flux, and so often these kind of details are swept under the rug, under the table, but that's what people are doing. They're imposing zero flux. When you have periodic, you wouldn't have to do that if you had actual walls. If you had walls, then you would have boundary conditions like the ones that we found here for psi. You would get boundary conditions for psi on the edge. But if you are imposing periodicity, you've left it to be quite free. You've said the same things are the same here as here, which is not really enough to completely specify the problem. And again, I say this because people often neglect this. If you have periodic boundary conditions, then you need an additional condition, a single scalar condition, such as to impose the flux.
That means no flux or no net flow or something.
No net horizontal flow, that's right. Now, in the two cases we discussed, the stress-free and the rigid boundary conditions, we already said this. In one case, you have the second derivative psi being 0, in the other case you have the first derivative psi being 0. And that's all you need for boundary conditions for psi in this two-dimensional case. And from now on, let's talk about the stress-free case where the second derivative is of psi 0. So this is a complete specification of the domain and its boundary conditions. So now we recall the equations that we came to last time. Here, yes, here, but now we dropped the bars. We recall that we had u dot grad u dot grad t, that we had a Prandtl number here, a Rayleigh number here, and let's go quickly back and go to those equations here. This is the temperature equation, the same one that you saw just now, and now we're going to rewrite it in terms of the psi instead of the u, and we recall that u is u has components u and w, which are minus dz psi and plus dx psi, and so writing this dot product, this advective term, you then find what's called a Poisson bracket. That is to say, where you're taking the two derivatives in one direction and the other. That is to say, here you have dx psi dzt minus dz psi dxt. So we're writing that as j of psi and t. And so we've just rewritten the equation in this way. And now this equation contains only psi's and t's. Okay, so we've reduced to two dimensions. The harder thing is the velocity equation. And so there's all these, there's more. Oh yeah, more, lots more. But this is not, you don't need anything other than knowing how to use vector identities to get to this. So let me just start. You have the velocity equation. One of the classic things you do in fluid dynamics, you take the curl of this equation so as to get rid of the pressure, because not only is the divergence of the curl equal to 0, but also the curl of the grad is equal to 0. So we do that. And in these two-dimensional settings, we take the y component of the curl. So when we do that, let's see what happens to the u in the simplest one. We have the curl of u. Well, u is itself a curl, and the double curl is minus the Laplacian. There's an extra term, which the div of the grad, which is not relevant here. Yes. So you're going, this term here is going to become a minus dt times the Laplacian. Of course, the pressure is going to, the gradient of pressure is going to disappear. Here, if you're taking the y component of the curl of something in z direction, that gives you minus dxt, so that's going to happen here. And then the curl of the Laplacian, and you're going to do lots of vector stuff, and basically the double curl, as we said, is minus the Laplacian, so this is minus double Laplacian. There would be things, other terms if it wasn't so simple, if there wasn't, if psi didn't, wasn't just in the y direction. So this u term has become minus Laplacian of psi. This green term has become minus double Laplacian of psi. And then, so if we take, and this t has become minus dxt, so it's natural enough to multiply the whole thing through by minus, which leads to a minus term here. Okay. And here's a little story, which is to say that when I did my PhD thesis, I did all this, but this is a very standard calculation, but what I did was I did not, I took all those minus signs away, but I didn't put the minus sign here, and I had this minus sign wrong for 6 months, and so this I will never forget here, the fact that you have minus, 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 okay, get rid of those minuses, but then put in a minus here as well, so there it is. Yeah, so this is one I will never forget. And now there's, this term here has the most complicated treatment. Remember that u is the curl of the stream function, and so if you do that, you go, and we're not going to go through that, but what we end up with is that this nonlinear term, this curl of the advective term, this is the advection of velocity by velocity, ends up being minus this same j, this Poisson bracket, this alternating derivatives between psi and Laplacian of psi. That's what's written in the last line here. We have a dz psi, dx Laplacian of psi, minus the opposite. And you'll be able to follow this through. Incompressibility is used, and this and that. Okay, so we end up with our final equation for velocity is all this. Okay, so we have our equation for temperature, which is here, and our equation for velocity, which is here. In both cases, we have this j, the Poisson bracket, and that's a nonlinear term. And so to do linear stability analysis, which is our next step, we will neglect this j, this Poisson bracket. Okay? So the same equations, but without the Poisson bracket. So let's get going here. Linear stability analysis, those same equations, but without the red terms. And so what can we say about these equations? I mean, well, how can we solve them almost immediately? Well, we know we have periodic boundary conditions.
Why do you delete the Poisson bracket when you use
You're taking away quadratic terms. The Poisson bracket is a quadratic term. The psi appears twice there, and and here the psi and the t each appear once, and hence these are quadratic terms. We recall that, okay, maybe I should say something specific. I'm linearizing about 0. I could be linearizing about a finite solution, in which case I would have to take the deviation of this, but I'm linearizing about 0 because this t is the deviation of the temperature from that linear profile. And the psi, we recall that the basic state was motionless. You had this layer of fluid which was hot and less hot and less hot until being cold here, and it wasn't moving. So linear stability analysis calls for writing terms that are only linear in small quantities, and which here are psi and t. The base state has them being 0, and the linear stability analysis has them being small. So these are the quadratic terms, and we are neglecting them. Okay, so here's linear stability analysis. Let me remind you then of the steps that this corresponds to in yesterday's class. You recall that we wrote, yesterday we wrote the general dynamical system, x dot equals f of x, and then we searched for fixed points which were x bars such that they didn't move. That was the fixed point. So this is the dynamical system, and this was a fixed point. And then we discussed how perturbations of x bar behaved. We had equation for x bar plus epsilon of t was equal to f of x bar plus f prime of x bar epsilon plus 1/2 f double prime x bar epsilon squared. I think everybody should be probably comfortable with this, even those who weren't here last time, right? This is, yeah. Okay, so what have we done? The finding of the base state, the one with the stars, was this step here, the stars, except we used stars, but then we non-dimensionalized. Well, anyway, that was what we did. Now, we're engaged in this step here, and let's simplify this. Of course, x bar doesn't depend on time, it's a fixed point, so we're talking about dt of epsilon, and this epsilon is this deviation that we're talking about from the star, from what we're talking about here in t's and size are the deviation from the fixed point, which is that motionless linear temperature profile state. So that's what all of our quantities here are effectively epsilon. F of x bar is 0 by construction. I shouldn't have plus, there's nothing to add it to. So we wrote this. And then we didn't consider these terms when we were doing linear stability analysis. So we just neglect this. This one is really equal to 0 by construction. And this one is assumed to be 0 because if epsilon is small, well then epsilon squared is even smaller. Okay? And that led us here. That led us to the very simple equation epsilon dot equals f prime of x bar epsilon with the solution epsilon of t equals e to the f prime x bar t epsilon of 0. And we said there is growth of this perturbation if f prime of x bar is positive, and there is decay if f prime of x bar is negative, right? And then we did all of this again in a many-dimensional setting where we ended up writing dt epsilon, where epsilon was a vector this time, and we wrote we had the same kind of thing, except that f prime became a Jacobian matrix, and you can take the exponential of a matrix, and we discussed that for a fair amount of time yesterday. This itself is a matrix, and so this is a matrix times a vector, and that's not nearly so simple as to say, well, is f prime of x bar positive or negative? What we concluded was that what we had to look at was the eigenvalues of this matrix, the Jacobian matrix. This is defined as, let's see, df of x bar. Its ijth components are dfi, dxj, all evaluated at x bar. It's the matrix of partial derivatives, and it had eigenvalues, lambda 1, lambda 2, lambda 3, and so on. And what we said was something would be stable if all the eigenvalues had negative real part, and it would be unstable if any of the eigenvalues had positive real part.